Now let's look at the relationship between principal components and variance. So we'll go back to our original rectangular data, and remember, before we can do anything, we have to center the data by taking the mean of each column and subtracting it from each of the values in that column. So here is our center data, and at first glance it might be a little confusing, but it's actually really easy to interpret this data. If we look at our first value in our first row, first column, the width 2.97, what that means is that that first observation was 2.97 greater than the mean for the width column. Similarly, the length was 1.35 greater than the mean length that we measured across all of those yards. And on the next row, the width of negative 3.03 is 3.03 meters smaller than the average for the widths that we measured for the 100 yards. So each entry is still in its original pre-centering units, so meters for width and length, and area, and square meters for area, and meters for perimeter. Okay, so let's first informally look at what singular value decomposition tells us. It gives us these matrices U, sigma, and V transpose. So let's look at the singular values that we see in our sigma matrix. So here we have our sigma matrix. We can see that the first column has a singular value of 197.39. The second has a value of 27.43, and the third has a value of 23.26, and the fourth is 0. So, informally, what we can say is that the ith singular value tells us how valuable the ith principal component will be in reconstructing our original data. So we can see here that the first principal component, 197.39, it's doing most of the work. And then the second principal component and the third principal component, they contribute equally. And the fourth principal component, it's 0, so it contributes nothing. And so that's why we know that we end up with a rank 3 result. Okay. Now, let's say I give you a 6-dimensional data set, and you do singular value decomposition on that, and you get back the singular values shown on this slide. What would you say is the most appropriate rank to use for our approximation by looking at this? So take a moment and think about it. Okay, well, if we just look at it, we know it can't be 6 because the sixth singular value, it's 0. And if we look at the fifth, well, it's 0.2, which is relatively close to 0. And especially when we look at the first two, they're really large, right? Relative to all of the other singular values. And so maybe it would be 2, right? Adding in those 4 additional principal components, it gives us some additional accuracy, right? If we add in all 3 that are non-zero, we'll get perfect accuracy, but we don't necessarily need all 3 values. So we could get most of the accuracy from just looking at the first 2 principal components. All right, so a little bit more formally. The ith singular value will tell us how much variance is captured by the ith principal component. So what we need to do is we first need to define the total variance for our data. And it's just the sum of the individual variances of each of the attributes. So in this case, we have 4 attributes: the width, the length, the area, and the perimeter. So the variance of the width is 7.7. Variance of the length, 5.3. Variance of the area, 338.7. And the variance of the perimeter is 50.8. If we sum all of those variances up, we end up with 402.56. Now, you can't compute that by just looking at the data that's here on the graph, because remember, our data set has 100 observations. So I use the notebook that's associated with this lecture to determine what the variances were and to sum them all up. Okay, so again, the ith singular value tells us how much of the variance is captured by the ith principal component. And that value is equal to the ith singular value squared over the number of observations. So the variance that's captured by the first principal component is 197.39 squared over 100, or 389.63. The variance that we capture in the second principal component is 27.43 squared over 100 observations, or 7.52. And finally, the variance that we capture with the third principal component is 23.26 squared over 100, which is 5.41. Now, if we sum up all of those variances, we end up with 402.56. But again, remember, that was actually the total variance that we had for our original data set. Okay? So now you can see the relationship between the variance that gets captured by the ith principal component and our overall total variance for our data set. So, to get a sense of, what's the relative importance of each principal component, you can compute the fraction of the total variance that's captured in each coordinate. So we're just going to sum up all of our variances, so 402.56, and we'll just look at what is the variance captured by a particular principal component. So 389.63, 7.52, and 5.41. So if we do that, we end up with an array that says 97% of the variance is captured in our first principal component. 2% is captured in our second principal component, 1% in the third, and nothing for our fourth. Now, why am I showing this? Because again, I asked you a question earlier, which was, what's the appropriate rank to use to approximate our data? And so this is the approach that you can use. You can compute the variance that's captured by a particular principal component, and then we can divide by the sum of the variances, and that'll tell us what the contribution is. Now we can actually plot that graphically. It's called a scree plot, and here's an example of it. And it's an interesting kind of plot because we can see that most of the value is in our first principal component, and the rest of the principal components don't really add all of that much additional value. Okay, so what we've looked at today is principal component analysis, as we've explored the impact and the value of each of the principal components. PCA is this process of linearly transforming our data to a new coordinate system, where in that new coordinate system the greatest variance occurs across the first dimension, and then the second greatest variance across the second dimension, third greatest variance across the third dimension, and so on. And so in our example here, we could see that most of the variance gets captured by our first principal component, and then a lesser amount by our second principal component, and an even smaller amount by our third principal component. And our fourth principal component is 0, so that captures no variance in our data.